Welcome back to our series on tensor calculus. Here in video 18, we're going to follow up our last video by analyzing the contravariant basis in each of our sample coordinate systems. As usual, we'll start with the Cartesian coordinate system. As a starting point, I've written down the two major equations from our last video. And what we're trying to do is to find, first of all, this guy, which is the contravariant metric tensor. And we're going to do that by starting with our covariant metric tensor, which is this guy right here. And of course, we know what the Kronecker delta is. So what we're interested in is finding the matrix that is the matrix inverse of this guy. Well, that's a trivial exercise. The inverse of the identity matrix is just itself. And so we can go ahead and fill that in here. So this guy is what we're looking for in this equation. So now that we have that, we can use it in this equation along with our covariant basis vectors up here to derive our contravariant basis vectors. So let's do it for Z1. Z1, contravariant basis vector Z1 will be equal to Z11 times Z1 like this. We're going to iterate through all three values of J here. We've got a dummy index, so we're going to have three terms, Z12, Z2, and Z13, Z3. But if you look down at our matrix here, you recognize that this term and this term are both 0. The only term that survives is this guy right here. And furthermore, this one is equal to 1. So after all of that, we conclude that Z1, our contravariant basis vector Z1, is equal to Z1, which is our covariant basis vector, both of which now are equal to simply x hat. Now if you continue this kind of analysis for the other two, you'll find the same is true for all of them. Z2 is going to equal Z2, which is equal to y hat, and so on. Therefore, we reach this conclusion that the contravariant basis vectors simply look like this. They are the same thing as the covariant basis vectors you see up above. Now, I'll remind you from the previous video that we have this relationship as well. Zi dotted with Zj, our contravariant basis vectors, are equal to Zij like this. So when we have I and j equal to each other, such as 1, then we'd be looking at this entry right here, and Z1 dotted with Z1, so this would be the square of the magnitude of Z1. So just like the fact that these elements here, if you take the square root of them, you'll find the magnitude of each of the basis vectors, the same is true here. Square roots of each of these terms will give us the magnitude of each of these vectors. And of course, they're just equal to 1 in this case. Now, when it comes to a linear combination, remember we said we could express any vector as a combination of contravariant factors times covariant basis vectors, or covariant factors times contravariant basis vectors. Well, in the case of Cartesian coordinates, since this is equal to this in every case, we have to conclude that this is the same as this as well. So in Cartesian coordinates, for example, we'd say that the vector component v1 in the upper position is identical to v1 in the lower position, both of which are identical to what we're accustomed to seeing, which is just the x component of a vector in Cartesian coordinates. So if you've never understood or heard of the difference between covariant components and contravariant components, it's very likely because of this unique feature of Cartesian coordinates. Namely that in Cartesian coordinates, all contravariant objects are exactly identical to their covariant counterparts. Now, although this is a very trivial result, it is also a very important one that we'll refer back to many times as we move forward. Okay, let's move on and repeat the analysis for affine coordinates. And as per this equation, we've got to find, first of all, the inverse of this matrix, the inverse of the covariant metric tensor. Now, the topic of inverting a matrix is a subject that would take up several videos just by itself, and that's not what we're about here. If you're unfamiliar with how to invert a matrix, then that's a topic you need to look up on the internet and go study. What I'll do here is just to tell you that for a 2 by 2 matrix there is a formula, and that formula is first of all to swap the order of the diagonal elements so that they become b squared, a squared. Then we take the off-diagonal terms and make them the negative value in each case, like this. And finally, we divide everything by the value of the determinant here. So the determinant will be a squared b squared minus the product of these two terms, which is minus a squared b squared cosine squared alpha. And it shouldn't be too hard to see that that is equal simply to a squared b squared sine squared alpha. So what we have to do is to divide every term up here with this factor. Now it's often easier to leave it in the form like this, where we have a factor outside. We've done the changes that I have up here, and rather than distribute that term into the whole matrix, you can just leave it outside as a factor like this. Or if you want to distribute it into the matrix, then this becomes the inverse that we're looking for. So what we're saying is that if we take the matrix here and multiply it by this matrix, you're going to get the identity matrix 1, 0, 0, 1. Now, I don't want to take the time to prove all of that, but I recommend maybe that you do that. Take this matrix, multiply it by this one, prove to yourself that it equals this. All right, so now we've got to take this equation and use it to derive our contravariant basis vectors. Okay, let's spell it out for the value of Z1. And this time we can't ignore any of the terms because none of the terms in our matrix are 0, so we're going to have to use the full formula. So Z1 is going to equal Z11 times the covariant basis vector 1 plus Z12 times the basis vector 2, covariant basis vector 2. Okay, now let's expand all of that out as per what we've got over here. We've got to say then that Z1 is equal to our Z11. Now I'm going to use this form of it. So let me start by just saying that we're going to have this expression. I won't write it out just now. It's this expression in front, and then we're going to take Z11, which is b squared, times our covariant basis vector 1, which is this, which becomes a x hat. So that's the first term. And then I'm going to take Z12, which is going to be this term right here, and multiply that by this guy. And we'll go ahead and expand that out as we go. So that's going to, the first factor using this is going to be minus a b squared cosine squared alpha x hat. That's what we get if we multiply this by this. And then the second term, we're going to multiply this by the same factor. We're going to get minus a b squared sine alpha cosine alpha y hat, like this. Okay, now I think you can see by inspection here that, again, we have this factor that we're talking about, this guy. I think you can see that we can combine these two terms to form a b squared sine squared alpha x hat. And of course we have the other term over here, ab squared sine alpha cosine alpha y hat, like this. And now if we go back and look at this term and divide that into each of the terms on the right, we're going to wind up with z1 being this term divided by a squared b squared sine squared alpha is just going to be 1 over a times x hat. And if we divide this whole thing by this factor, we're going to get negative, what do we get here? Cosine alpha over a sine alpha y hat. So this becomes our z1 basis vector. Okay, we've got to do the whole thing again for vector 2. And z2 then equals our factor 1 over all this guy right here. And we're going to take this time z21, which is this factor right here, and multiply that by z1. So that's going to be negative a squared b cosine alpha x hat. Then we're going to have to multiply z22, which is this guy, by each of the terms in here. So that's going to be plus a squared b cosine alpha x hat, and the same term, a squared multiplied here, is plus a squared b sine alpha y hat. All right, I think you see these two terms canceled out, and so what we're left with is that z2 is going to be this term divided by this expression, which is simply going to be 1 over a sine alpha y hat. And that becomes our covariant basis vector number 2. Okay, let's move that up a little bit and see if that's the right result. Drop those in place, and yes, you see this guy right here, and you see this one right here. All right, that was rather painful. Okay, finally, we take the diagonal elements here, find the square root of those, and these now are the lengths of our two contravariant basis vectors. Now we said that there's a reciprocal nature between them here. Let's look at that. If you look at these guys and compare them down here, you'll see that there are sort of reciprocals, not exactly. You've got a and b, whereas down here you've got 1 over a and b, but there's this factor of sine alpha. Now the reason that they're not exactly reciprocals is because z1 covariant basis vector is not parallel to the z1 contravariant basis vector. They occur at an angle. So if the dot product of z1 and z1 has got to be 1, then this sine alpha factor adjusts for the fact that these two are not parallel to each other. Okay, there's a lot going on here, and I'm sure you'll want to go back and repeat this on your own to make sure you understand it. But in the meantime, I think the best way to understand it is to go over and look at a short demo with our graphing software. Here we have affine coordinates. I've currently got the skew angle set at 60 degrees, and both scaling factors are equal to 1. Now you'll recall that the covariant basis vectors look like this. They lie along the grid lines, and because the scaling factor is 1, they're both unit vectors at this point. Now let me display what the contravariant basis vectors would look like. Notice the relationship. Contravariant basis Z1 is perpendicular to covariant Z2. Remember, that was one of our requirements. Contravariant basis vector 2 is perpendicular to covariant basis 1. So those limitations set the direction of our new vectors, and then the length is determined by the fact that the dot product of the Z1 vectors together has to be equal to 1. They're reciprocal to each other. So the first thing I'll do is show you what happens when we change the scaling factor. Notice as I increase the scaling factor of one, the other decreases. And the same is true if I change the scaling factor of the second. So you get the idea that they are reciprocal in nature. Now we said that the contravariant basis vectors would form just as valid a basis as the covariant version. So let's demonstrate that. First of all, let me clean this up a little by taking off the display of the grid and the angle. Now I can introduce two additional axis lines, one of which is parallel to our new vector z1, the other is parallel to our new vector z2. Then I can draw parallel lines back to these axes so that we get something that looks like this. So now the same point P can be represented in covariant terms as coordinates of 2 and 3, but using the contravariant basis, the same point would be located at 3.5 and 4. And of course I could also construct a grid here like this. So the point is we can use the red vectors just as easily as we can use the blue ones to define a basis in our coordinate system. Now let's throw a vector into the mix. You'll remember we had a vector like this in a vector field, and we said that we could represent this vector as a linear combination using our covariant basis vectors. And if you recall, it would look like this. Our linear combination is to take 3.3 times z1 here, add 3.5 times z2, that's two vectors, add them together, we get this. But we could do exactly the same thing using our contravariant basis vectors. And that result looks like this. We could take 5.1 and multiply it by z2, 5 times z1, we get two vectors, add them together, we get the same resulting vector. Okay, so let's hold this picture just a bit. Let me slide it over a little. And let me show you what this looks like as we change well, let's change the skew angle a little bit. You see how that picture changes as we change the skew angle. We'll set that back to 60, and then I'll show you what happens when we change the scaling factors. We'll change the scale of 1 and then of 2. And notice as we go through this, the values of the coordinates, the vector component lengths all change, but the vector itself does not change through any of these actions. And the last thing I want to show you is what happens when we reset the scaling factor back to 1, which I've done here, and now I want to change the skew angle to 90 degrees. And when we do that, both sets of vectors collapse and collide into the same thing. The two z1 vectors become exactly the same thing, z2 becomes the same thing, the two sets of axes align together, everything's right angles and perpendicular, and of course we've just collapsed into the Cartesian coordinate system, where the covariant and contravariant bases are exactly the same thing. Okay, hopefully that demo was useful to you. We need to go back now and take a look quickly at the other coordinate systems. Now, given what we went through with affine coordinates, you're going to be pleasantly surprised to see how easy it is with plane polar coordinates. So when we start here, of course, we need to find the inverse of our covariant metric tensor. Well, because it is a diagonal matrix, it has no off-diagonal terms. To invert that, all you do is to invert each of the terms along the diagonal like this. You can prove to yourself that if you multiply this by this, you'll get the identity matrix. So we're done there. The next thing is, because there are only diagonal elements, this formula becomes very simple as well. For example, Z1 is going to be equal to our Z11 term down here times covariant basis vector 1. We need not consider Z12 because that's equal to 0. Likewise, Z2 is equal to Z22 times Z2. You'll find that this relationship is true anytime you have a diagonal matrix relationship such as we have here. So finding our contravariant basis vectors is very simple. We simply take the covariant basis vector, multiply it by the Z11 term, and that'll give us the contravariant basis vector. Here we take this guy, multiply by this, and we'll have Z2 being our contravariant basis vector there. So here are the results we're looking for. So compare them. Notice that these two are equal because of the factor 1, but here if we take this guy, multiply it by this, we'll get this. And finally, if we take the square root of our diagonal elements, we'll find the magnitude of our vectors. Now notice in this result that these vectors are truly reciprocals of each other. Here they're 1 and r, here they're 1 and 1 over r. Now the reason they turn out to be true reciprocals is because Z1 as a covariant vector is parallel to Z1 as a contravariant vector. The same is true of Z2. Z2 here and Z2 here are parallel to each other, and because they're parallel, the relationship is that of a true reciprocal. Now let's take a minute to see what this looks like with our graphing software. You'll recall that in plane polar coordinates, our covariant basis vectors look like this. Z1 is just a unit vector pointing away from the origin. Z2 is at right angles to the circle, and its length is equal to the length of the radius itself. Well, the contravariant basis looks like this. Z1 is also a unit vector pointing in the same direction as the covariant counterpart, but Z2 is the reciprocal of the one that's tangent to the curve. That means that as we make the circle smaller, this vector gets larger. So when we get to 1, it's a unit vector, but when we get to a half, it's equal to 2. All right. Now what we'll do is to add our vector. Remember, we're doing a sample of a vector field that has a constant vector everywhere. So as I move the point around, the vector doesn't change. If we wanted to represent that in covariant terms, we'd use the covariant vectors, and it would look like this. So here you see the contravariant components that would be combined with these vectors to provide the linear combinations. Now if we wanted to do it with the contravariant vectors, it would look like this. Here we're using covariant components combined with contravariant basis vectors. So either system works. And finally, let me put up both systems at the same time. And it gets a little cluttered, but I just wanted to show you what happens when we change the scaling factor of r. And you can see that the two basis vectors pointing in the z1 direction are simply reciprocals of each other. All right, I think you see how this works. Let's go back and finish up with our last two coordinate systems. Our last two examples are going to be really easy. With cylindrical polar coordinates, because the covariant basis vectors are mutually orthogonal, we have only the diagonal elements in our covariant metric tensor. And so to invert that, we simply invert each of the factors respectively like this. And again, because they're mutually orthogonal, In order to find our contravariant basis vectors, we multiply each of these by each of these factors respectively. So the Z1 contravariant basis vector and the Z3 contravariant basis vectors will be the same as these two. This one we will multiply by 1 over rho squared to get the Z2 contravariant basis vector. And the results are as you see them here. Okay, and finally, we take the square root of the diagonal elements to find the magnitudes of our vectors. And as you can see, these are truly reciprocals of the covariant basis vectors. And that's all there is to it. And finally, for spherical polar coordinates, we just repeat the same drill. In order to invert this matrix, we simply invert the corresponding diagonal terms like this. Now to find the contravariant basis vectors, we multiply each of these by these diagonal elements, and what you'll come up with is this. Here we've divided each of the covariant basis vectors by each of these respective terms, and this is what you get. And finally, here is the list of magnitudes, which again you'll notice are true reciprocals of the magnitudes of our covariant counterparts. And that brings us to the end of this video. Hopefully you now have a much better understanding of what the contravariant basis vectors are all about.